Hey guys, so in this video we're going to start talking about buoyancy, which is the thing that causes objects to float or be pushed up when in a liquid. Let's check it out. Alright, so if you have an object that is immersed in a liquid, the object will be pushed up by a force called buoyant force, and buoyant force comes from the fact that the physical phenomenon responsible for this is called buoyancy, right? Which usually is associated with floating. And because this is buoyant force with a B, we're going to call this FB. Now, the reason this happens is because of a pressure difference between the top and the bottom of an object that's under a liquid. So let's say you have a box that is completely submerged, completely underwater, and we know the water is going to push on all sides, right? The water is going to apply pressure on all sides. And pressure is associated with force. So if there's a pressure, there's a force. Now, the force on the left will cancel the force on the right because they are at the same height. For every force on the left, I can draw an equivalent force on the other side on the right that will exactly cancel it. So the side forces don't do anything, but the top and bottom forces will be different because the top and bottom pressures are different. And we know that the deeper you go under a liquid, the greater the pressure. So the pressure at the bottom over here, at this point, is greater than the pressure at the top. Therefore, the force with which the liquid pushes up on this box is greater at the bottom than it is at the top. And the difference between these two forces is the buoyant force. Okay, so you're always going to have a stronger force up than a force down. So the net buoyant force is going to be up. Cool. And so that's thing number one. Thing number two you need to know, and you probably should memorize this, is Archimedes' principle. He figured out that the magnitude of this buoyant force is the same as the weight of the liquid displaced. Okay, so you should memorize that quote because that could show up in some way, and it's important to know that it's a big principle in physics. Now, the problem is that this quote here doesn't really help you calculate this force. So I'm just going to give you the equation. If you were to sort of translate this quote into a physics equation, you would get that the buoyant force is the density of the liquid, gravity, 9.8, or whatever planet you're on, and the volume of the object that is underwater. So I'm going to call it rho liquid, G, and V under. So there's two really important things here, distinctions to make. In this equation, the density that matters, the density that you should be looking into, is the density of the liquid. Even though the object is inside, and this is the force on the object, the density that matters is the density of the liquid. Don't get that messed up, okay? And the volume that matters is the volume of the object, but only the amount of volume that is underwater. So it's the volume under water or under the liquid. Okay? Or the volume submerged of the object that is submerged or immersed in the liquid. Okay? I'm just going to call it under to keep these words simple. And it's not necessarily the entire volume, unless, of course, you are entirely under. So let's think about this real quick. The idea here is that the more of an object is underwater, the stronger the force. And you might play this out in your head and just sort of imagine that if you're getting a piece of styrofoam, as you push it down under water, there's more resistance, there's more force pulling it up. And that's because the more volume you have, the more buoyant force you have. Okay? So that's that. And then one last thing I want to remind you, because you're going to be using this a lot, is the density of an object. The definition of density is mass over volume. So the density of the object will be the mass of the object and the total volume of the object. So I'm going to write V. I'm going to write actually mass total. It's the entire mass. Whoops. It won't go away. It's the entire mass of the object divided by the entire volume of the object. And the reason I'm being careful with that distinction is because you have volume under, which isn't necessarily the entire thing, and you have volume total, which is the entire thing. And we're going to be using these two equations all the time to solve these questions. Okay, the last point I want to make, and we're going to do an example here, is that almost every single buoyancy force problem is just a force problem. So it's just a good old F equals ma problem. We could have done this right after you learned F equals ma in some ways. And also that most of the time, it's going to be even simpler than F equals ma, because most of the time the objects will be at rest, meaning the velocity is 0, and they will be in equilibrium, which means the acceleration is 0, and the net force is 0. So it's really an sum of all forces equals 0 problem most of the time. It's just equilibrium. Forces are just going to cancel. Cool? So let's do a quick example here. So it says when an object of unknown mass, so we don't know the mass, and volume, unknown volume, we don't know the volume, great, is fully immersed. Let me draw that. Fully immersed means you're entirely underwater. Remember I told you there's two kinds of volumes, right? There's volume under and there's volume total. Because you are fully immersed, this means that volume under equals volume total, okay? In a large water tank and released from rest, it accelerates up. So when you release the object, it's going to accelerate up. And then it says once the object reaches equilibrium, 30% of its volume is above water. So here's the object. It's going to, eventually it stops up there. So when you release it, accelerates up. Eventually it stops, and 30% of the object is above water. Okay. Now, if you remember on this equation here, the only two volumes that matter are the total volume and the volume under. So 30% above doesn't do anything for us. What you really care about is the volume under. So you're going to change that into 70% under. That's one of the things that you have to do in these questions, is you always want to know the volume under. That's what matters. Okay. Now, with just that information, we want to calculate the density of this object. So what is rho object? Cool. Now, again, all these questions are going to start with F equals ma equals 0 because you are at equilibrium. So I'm going to write that the sum of all forces equals 0. And remember, the way to solve force problems has always been to draw a free body diagram and then write F equals ma. So let's draw a free body diagram. What's going on here with forces? Well, this object is here, so there has to be an mg pulling it down. And the new thing here is that because it's under a liquid, it's going to be pushed up by a buoyant force. And FB is always going to be up. Okay, let me write that here, just so you have it always up, because the density down here is stronger as you go lower. Cool. So if this system is at equilibrium, if the object is at equilibrium, it means that the forces cancel. So you can simply write that FB equals mg. The next step is always going to be, or almost always going to be, to expand this FB. What do I mean by that? We're going to rewrite FB based on its equation, which is this. So instead of writing FB, I'm going to rewrite it as rho GV. Cool? So let's do that. Density, remember, of the liquid, gravity, and volume under equals to mg. Right away, G cancels, and this is going to happen quite a bit, not always, but quite a bit. And we want to know the density of the objects. Now, if you stop for a second and you look here, you will see that density, rho, object, isn't anywhere in this equation, right? It's not here. You have density of the liquid, but that's not what we want. So it actually is here, but you have to look a little bit more carefully. It is going to be inside, hiding inside of one of these things here, right? Are there any of these things that you can rewrite to make this variable show up? And there is, and I warned you about this, that we were going to be using this equation all the time. So very often you're going to rewrite things to make variables show up, okay? So the way we're going to do this is density of the object is mass total divided by volume total. Therefore, mass total is density of the object times volume total. All right? So what we're going to do is we're going to replace mass with density volume, and now we're going to have our variable there. Okay? So the density of the liquid times volume under equals density of the object, which is what we're looking for, that's good, times volume total. Cool? Now, realize also that we know the volume under, okay? We know that we are 70% underwater, so I can rewrite volume under as 70% of, or 0.7 times, volume total, okay? Just rewriting this here. So if you do that, you can cancel these two out, and then we are basically done. The density of the object is 0.7. The density of the liquid, we are in water. We're in water, so this is just 1,000. So the density of the object is 700 kilograms divided by, or per cubic meter, okay? It makes sense, it should make sense that the object is floating above water because it is less dense than water, therefore it rises to the top. I want to talk about one last thing here. Notice here that I had said that the volume under the water is the same as the total volume, but that was before you released and the object moved this way here. Now the volume under is less than the volume total because some of it is above. Cool. That's it for this one. Let's keep going.